We have executed a project with ISRO, so that was on developing cryogenic temperature sensor.
As we know that you are awarded by DRDO for this technology of TNG shoes that you have developed in your lab, it became so popular in the media as well.
We delivered close to around 15 prototypes to DRDO.
Okay.
So we received some good comments from them. Now they are looking for more support. So basically they had requested that in another 2-3 years we may need to supply close to around 300 of those shoes.
As we have seen, you have developed some soft robots in your lab.
We have developed 2 soft robotic structures. One in collaboration with TAH, IIT Guwahati, where we had developed a small SMA-based jellyfish kind of structure.
Yeah.
And we have also developed a SMA-based turtle that was in collaboration with DYS, Smart Materials Laboratory, DRDO. We work on this concept called shape memory alloys. These shape memory alloys, basically when you have a spring, when you try to expand the spring, you can bring back the spring to its original state by applying a heat to it. So this is a kind of a fundamental capability of the material. Like you might have heard about a sunflower tracking a sunlight.
Sir, as you're using the made in India materials for the fabrication purpose, are these materials commercially available?
Commercially, when you try to get these materials are either available in the form of a wire or in the form of a rod, or sometimes it is in the form of a sheet. What we have done is, so we have been working on tailoring these shape memory alloys based on the functionality.
Thank you so much, sir, for sharing this detailed information on your technologies that you have developed. I mean, you have so many of the technologies to talk about. I think just one session is not enough for all of this. Hello everyone, welcome to the third episode of IIT Indore's InnoQuest Talks 1.0, where intellect meets innovation and thinking fuels invention. Today, we are coming up with a very interesting and exciting technical discussion with Professor Palani from the Department of Mechanical Engineering. He has significantly contributed to the technological development. He is a visionary in his field and we are honored to have him here today with us. Before we engage in listening to his interesting innovations, I take pleasure in introducing Professor Palani. Professor Palani completed his PhD from IIT Madras and postdoc from Japan. He joined Mechanical Engineering Department of IIT Indore in January 2012. During his experience of about 13 years in the institute, he occupied multiple positions in the institute, national and international levels. He served as Dean R&D from 2020 to 2025, Head of Mechanical Engineering from 2018 to 2020, and Head of Discipline of Metallurgy and Material Science and the Center of Material Science and Engineering from 2014 to 2018. His research interests include mechatronic system design, soft robotics, manufacturing engineering, laser-assisted micromachining and surface engineering, smart materials and structures, shape memory alloys, and so on. He has executed around 20 sponsored projects which are funded by different government organizations like DRDO, ARD Pune, ISRO, and so on. And also the 8 consulting projects totaling to a worth of around 12 crore. He has 6 granted patents and 9 filed patents. He is the author of 11 books, chapters in the books, and monographs, and also edited 2 books and monographs. He has also developed a few facilities catering to the research and teaching. He has developed 5 technologies and some of them are translated as well. On the top of it, he has 175 international journal publications. He has also received 13 awards and he is the mentor to numerous researchers. I'm very much excited to welcome Professor Palani for a discussion on our technical podcast. Without his support, this wouldn't have been possible. A warm welcome to you, sir. Thank you for joining us today. First of all, we would like to know about this lab, which is Mechatronics and Instrumentation Lab that we are sitting here. So we would like to hear from your end.
Yeah. So actually this lab was started in the year 2012. So ideally, this lab was focusing towards instrumentation and control for undergraduate students. So earlier there was a course on microprocess. So we updated that course to instrumentation and control with the lab and theory. So that the main motto is the students should get a hands-on experience on the different instrumentation and they should also have a capability to develop certain instruments. So in fact, as a part of the course, so we also have this small project where students are involved in making some small prototypes, small instruments for different applications, small micro robots, etc. So that's how this lab was initiated. Then slowly we were catering the mechatronics system design for MTech advanced manufacturing and production industrial engineering. So we focus on actuators, sensors, control system. So we have also developed a setup for optomechatronic system design, so that students get trained in those particular technologies. And there is a provision for having a kind of a hands-on experience on different areas. So this is with reference to teaching perspective point of view. With reference to research perspective point of view, so we could get quite a good amount of funding in the areas of developing smart materials for different functional applications related to mechatronics and related to instrumentation and control. So these are the equipments which are being funded from different funding agencies.
So all the instruments are almost funded.
All the instruments are funded from external agencies, like either from SCRB or from DST. So some are funded from DRDO and ISRO. So we have also received some funding from some private organizations also, like Volvo Eicher under a different scheme, under Uchchatra Avishkar Yojana scheme. And we have received some funding from Daimler for establishing these facilities.
Okay, that's great. Again, sir, as you refer to the smart materials, so how the smart materials are different from the conventional materials?
Okay.
We would like to know the differentiation between these two, how they are categorized basically.
Okay. See, actually, these smart materials are like they behave in a slightly in a different way. Like, let me just give you an example. So we work on this concept called shape memory alloys. So these shape memory alloys, basically, when you have a spring, so when you try to expand the spring, you can bring back the spring to its original state by applying a heat to it. So this is a kind of a fundamental capability of the material. Like you might have heard about a sunflower tracking a sunlight. So this is a kind of a biomimicking capability of this particular sunflower. So similar to this, these materials also has a specific capability which you can tailor these materials for different applications. So as far as these smart materials are concerned, so there are wide varieties of smart materials are there. So they get actuated with reference to different actuation medium. So in the case of shape memory alloy, we go for this heat-based system. In certain cases, it can be also based on magnetic-based systems. So there are some piezoelectric materials are there. There are some triboelectric materials are there. So which we try to develop it over here, catering towards different functional applications.
Okay.
That is the key motto of this particular laboratory. So ideally, we start from the material development. So we focus on the characterization, and we develop a device, and we work on the reliability and life cycle behavior of that device, so that those device can be efficiently used for the market, has a market potential which can be taken up by a buyer. So that is what is the overall chain of flow of process we follow in this lab.
Okay. So as per their role in the strategic areas, how are the smart material transforming the defense, aerospace, or say energy sector?
Yeah, like there is a huge requirement of these smart materials, especially in defense and space related fields, as far as energy related applications also. Like in fact, the work which we were working with Volvo Eicher was developing a small heat engine. So where we were developing a shape memory alloy integrated heat engine. So from the exhaust heat, we were trying to create a kind of a heat engine. So it can be connected with the fan, and then it can be used for quenching the heat. So these are some kind of prototypes which can be developed. Now, when we try to look into this material perspective point of view, this material is highly sensitive, and then these materials strategically, so it has its own novelty, and it is very difficult to get. So in fact, that was the key motivation for starting up this work over here. So we started developing our own materials for different applications.
Okay.
Especially the first project, when we had an interaction with DRDO, so it was developing a kind of a aerofoil structure. So we were trying to develop a kind of 30 centimeter aerofoil structure, and these aerofoil structures gets actuated with reference to different. Basically, it was developed for a kind of a handheld missile. So we were developing these aerofoil structures. So what we did is we had these silent actuators, these shape memory alloys, integrated into these aerofoil structures, so that when you try to actuate it, you can create a high frequency systems. So that's how the work started. With reference to defense perspective point of view, or with reference to missile perspective point of view, for this intelligent nozzle development, such kind of materials are heavily used. In fact, on a defense perspective point of view, there is a huge technology has been transferred from NAL to defense for developing such kind of materials. So it is on a larger scale. So we are trying to cater on a smaller scale, where it can develop, we can develop a prototype out of it.
Mm. So as we have seen, you have developed some soft robots in your lab. So how are they different from the conventional ones?
Okay. See, as far as these materials are concerned, this basically I work on shape memory alloys. So these shape memory alloys, with reference to actuation perspective point of view, for example, if you want to develop a kind of a robotic arm, so you may need to look into the dynamics of it, and you may need to appropriately incorporate motors in it.
Okay.
So when you have a motor at the joint, so it will load your control system. So what we are trying to do is, these kind of shape memory alloys, since it has a biomimicking capability, it becomes a kind of a silent actuator.
Okay.
So your entire arm motion can be mimicked by these shape memory alloy structures. So only thing is, we may need to make a tailor-made structures, and we may need to program the material based on this biomimicking capability. So that possibility is there. So in fact, it started with developing a small soft robotic structure for underwater applications. So in the case of underwater applications, most of the cases, motors are used, where it tries to actuate the thrusters. So when it actuates the thrusters, it creates quite a good amount of noise, and it might be a point for noise getting picked up by the enemy rigger. So the thought process is, in fact, this idea came from DRDO. So they were looking for a kind of jellyfish kind of structure, so that this jellyfish kind of structure can be developed using a SMA actuated fin. So this will be programmed in such a way that the movement of the jellyfish will be almost biomimic, and the entire onboard controllers will be placed at the head. So it can go up to a 3-meter depth, and it can be used for surveillance applications, etc. And since it almost looks like a jellyfish, and since there is no noise is coming out of it, so it has quite a good amount of advantage. So the major advantage of these materials is, it has a biomimicking capability, and it is also called as a silent actuators. So, that is a key advantage of developing such kind of soft robotic structures. So we have developed 2 soft robotic structure, one in collaboration with TAH, IIT Guwahati, where we had developed a small SMA based jellyfish kind of structure, and we have also developed a SMA based turtle. That was in collaboration with the DYSL, Smart Materials Laboratory, DRDO. So we have developed and given the technology to them. So further investigations are in the pipeline.
Yeah. So again, this SMA-based turtle is again similar to the jellyfish.
Yeah. Only thing is, the biomimicking capability will be different. So in the case of a jellyfish, I may need to work in a frequency of 10 to 15 hertz, whereas in the case of a turtle, it is sufficient for me to work in the range of 2 to 3 hertz.
Okay.
So that is one. So accordingly, I may need to program it. I may need to develop the actuators, and I may need to develop the control strategies.
These two are different ones.
These two are completely different. With reference to functionality perspective point of view, they are designed appropriately.
Okay. Yeah. And sir, as you're using the made in India materials for the fabrication purpose, so would you like to talk about this? How are these materials commercially available?
Okay. See, with reference to functionality perspective point of view,
Yeah.
like these materials are highly restricted with reference to composition and with reference to the geometry. Like commercially, when you try to get these materials are either available in the form of a wire or in the form of a rod, or sometime it is in the form of a sheet. So what happens is it is very difficult for us to use these commercially available material for our applications. So what we have done is, so we have been working on tailoring these shape memory alloys based on the functionality. So first thing is we have gone to the fundamentals of shape memory alloys, where we could observe that we are selecting two working window. So if I want to develop an actuation in the range of 80 to 130 degrees Celsius, so I may go for nickel titanium based combinations. So if I want to work on 250 degree or more, so I work on copper based shape memory alloy based structures, because commercially copper based shape memory alloys are not available. So what we thought is we developed our own machines. So these are the machines which are like, we have given the design to an Indian manufacturer, and he has developed these machines so that these machines can cater the tailor-made shape memory effect. Like one of the key aspect of these machines is these machines are like when you are depositing, you can program it. So that is one advantage. Otherwise, what you may need to do is you may need to develop the material and you may need to program it separately. So here that is not the case. You can program it as and when, like the required actuation can be trained during the deposition.
Okay, so real-time kind of.
Real-time kind of deposition. And we have also come up with this concept called bimorph. So this bimorph is a good technology where in most of the cases you may need to train the shape memory alloy, like you may need to go from like a different life cycle behavior, like almost like you may need to reach close to around 600 degrees Celsius, and then you may need to quench it. So what we thought is we have developed a kind of a concept where we have integrated the shape memory alloy with a Kapton polyimide, so that we can improve the frequency of these materials. So we have developed a small Stuart platform kind of arrangement for this mirror steering applications. We have also developed an intelligent mirrors out of these shape memory alloy bimorph. And for this energy harvesting related applications, we have developed a SMA based pulley kind of arrangement, so that these pulleys can expand and then we can harness the energy. So that capability is there. And the most important point is like we can tune the composition. So the lab has a facility to develop a composition based on the requirement, and we also have a characterization facility to characterize the required aspects what we are looking for. So those capabilities are available with us now, which we have developed in the lab itself. In fact, for DRDO recently we have also developed a small shape memory alloy based fasteners. So basically those are kind of 3D printed fasteners. So we have developed a kind of a 3D printer, basically focusing on developing bulk shape memory alloy structures. So for bulk as well as thin film, so we have our own in-house capability to print the structures or fabricate the structures.
Okay. And so the way NASA uses SMA-based materials for different strategic applications, and I understand that it has a potential application in Indian space as well. So how exactly are you contributing to this one?
Okay, so we have executed a project. We have executed a project with ISRO. So that was on developing this cryogenic temperature sensor. So cryogenic means basically at a low temperature conditions, below minus 180 degrees Celsius. So ideally these like liquid nitrogen etc. are used as their fuel, where they would like to measure the level as well as the temperature sensing. So like what we have done is, so we have worked on developing a copper based shape memory alloy which can sense the temperature at these low temperature conditions. So we have made a composition and we have developed a kind of a fixture through which we have coated on an optical fiber. And so these optical fibers can be immersed inside these particular low temperature conditions. Based on the temperature gradient, it can actuate. So like it's a kind of a real-time system which we have developed. So the technology is was sponsored by ISRO LPSCB. So we have given the samples and everything, and we have also filed a patent. We are in the process of filing a patent with them. So furthermore are in the pipeline. In fact, now some kind of compatibility tests are going on with ISRO. So there is a potential towards like realizing a sensor for a live demo is available for it. It is in stage. processing
Okay,
stage.
so as we see that you are closely working with ISRO, so can you spread some light on the capabilities of your lab towards catering the needs of ISRO?
Yeah, actually, like we have also developed this system called thin film based micro 3D printing. Like normally in the case of additive manufacturing, most of the additive manufacturing relies on the feedstock what we are using. So since as far as this material is concerned, it is limited. Its feedstock is
Yeah.
limited. So and we have a capability towards thin film. So we have developed a technology using thin film as a feedstock, we can print the structures. So, I got an opportunity to demonstrate this technology to ISRO, and they have given some inputs, and they had requested us to print some piezoresistive sensors, basically silicon carbide based piezoresistive sensors.
Okay.
We have developed, we have printed, and we have given to them. So, currently on service basis, we are supporting some of the aspects related to for ISRO, based on their requirement. So, one of the requirement is towards laser cleaning of their samples. So that also we are participating in the process of cleaning their samples before electron beam welding. And we are also now in the process of printing strain gauges for space related applications. So that work is in the pipeline.
Okay, so you are so much into the work with ISRO.
Mostly on like a kind of a problem solving. We are trying
Okay.
to address those issues.
One just last question, and which is very interesting one. As we know that you are awarded by DRDO for walk to charge technology, and this technology of TNG shoes that you have developed in your lab, it became so popular on in the media as well. So we would like to know more about this one, sir.
Yeah, actually, this work almost started during the COVID time. So there was a kind of workshop which was initiated by DRDO and IIT Indore. So where we had an idea of this. In fact, I presented this idea on this walk to charge technology. So immediately they requested for a 2-page proposal, and we got that proposal funded from ARDE Pune. So, earlier, DRDO was working on this integrating a piezoelectric inside a shoe sole, where they found that those are a bit heavy. And it was since it's a ceramic, it breaks also. So so we came up with this concept called this triboelectric nanogenerators. So basically, it's a kind of an electrostatic charge generation. So we have tailor made these materials so that these materials can be easily integrated inside the shoe sole. And ideally, if you see, you get quite a good amount of charge. In fact, during the cold time, we could observe that sparks are coming out of the woolen cloth. So you can see a visible light coming out of it, but normally it won't harm.
Yeah.
The reason is it has a high voltage but less current. So we have tailored these materials, and we have developed a small circuit also, so which can convert the voltage into an appropriate current, and we can power up some devices. So in support with the ARD Pune, so in fact they gave a lot of inputs related to this integration, and we could develop a final product, a final prototype. So we delivered close to around 15 prototypes to DRDO. So we received some good comments from them. Now they are looking for more support. So basically they had requested that in another 2-3 years we may need to supply close to around 300 of those shoes, and they have given some requirements also. Now we have received some inputs from industries, so shoe manufacturers. So we are in the process of technology transfer, and we are also in the process of collaborative approach of developing this product. So probably in the next 2 years, we are expecting that it will reach the market, especially for defense-related applications.
Defense-related applications. Any other applications to this particular technology, sir?
We have extended this particular technology for kind of industry 4.0 related applications also. There are, you might have heard about legacy machines. So legacy machines are machines, basically they are pretty old machines. So they are catering many small scale industries. But it is very difficult to develop a sensor for those machines. So we are trying to develop some kind of sensors using this technology so that we can integrate it in this legacy machine. So one good example is this handloom industry. So handloom industry has a handloom machine which doesn't require any kind of power. So basically, based on the manual movement, they try to be. So we are trying to create a digital twin for it by using this particular technology. Because this is a kind of this sensor it's a kind of a self-energized sensor. You don't need to have an additional battery to it. So we are trying to integrate it with this handloom weaving unit, and we are trying to develop Industry 4.0. So that is currently in process.
Okay.
And more machine tool condition monitoring process we are working upon. Like one is for hydraulic power packs also we are working. And recently we are also focusing upon this early Parkinson detections. Already, since we have quite a good amount of data from the shoe sole, so we have generated a kind of a machine learning model, so which gives a overall gait analysis. So based on the gait analysis, so we would like to predict this early Parkinson detection. So that work is in progress.
Okay, so means in healthcare sector
Healthcare
as well,
sector, we are trying
this
to
TNG shoes will be
useful. So that is in pipeline. So we are
Okay.
working on it.
Yeah. Thank you so much, sir, for sharing this detailed information on your technologies that you have developed. I mean, you have so many of the technologies to talk about. I think just one session is not enough for all of this. Thank you so much for taking your time out.
Okay. Thank you.
sir.
Thank you.
To our viewers, we hope you gained valuable knowledge from Professor Palani's expertise and his various technologies. If you are interested in technology transfer, feel free to reach out to us via the email displayed on the screen for collaboration opportunities also. InnoQuest Talks 1.0 will continue to bring more engaging discussions on research, innovation, and technology at IIT Indore through our YouTube channel InnoQuest Talks at IIT Indore. Until next time, keep innovating and keep exploring.